go. Anthony, please.
Thank you. You are very welcome to this special meeting of the Royal Academy of Engineering of Spain. Due to the sanitary situation, for the last few years, we have been trying to get in touch with our society, our fans, friends, and followers. But it was difficult. Then we organized this type of meetings through internet. No? We have been dealing with all the important subjects for society: energy, climate change, CO2, COVID, education, development. We were very surprised with Africa. We were in touch with important politicians from Africa, and they told us that there's supposed to be 3,000 million inhabitants, 3 billion for Americans, 3 billion more than China and India together. We're going to have this problem with 3 billion inhabitants in Africa, that is, 10 kilometers from Spain. 10 kilometers from Spain. No? Then we have to do something to help them, because if Europe and the rest of the world, we don't help Africans, they are going to conquer Europe. They are coming by thousands every day. But if they are 3 billion and they are coming here, Europe is going to be in trouble, because we don't have enough food, we don't have enough universities, we don't have enough transportation. We have to do something before it happens. And then I think that one of the weapons, the tools that we have, is the quantum computation. And today is a very important thing, that because maybe with this tool that you are developing now, we'd be able to resolve the problem that we have many problems, but with the African problems that we didn't realize this, is going to be even bigger. Then maybe through you and your technology, we'll be able to fulfill the 17 goals of the development and also the problem that we have with Africa. Now, I'm going to give you the floor to our academician. Feel free. I suppose that your name is very difficult for them, no?
Yes, Sophia is quite difficult. Don't worry.
Now, thank you very much. Juan.
Thank you, President. Okay. So, and let me start thanking for the presenters and the participants, the 3 leaders in quantum that have accepted to be here with us today and are going to be the core of our conversation. I would like to thank Professor César Dopaz, who is also a member of the Academy, because he shared with me the pleasure of organizing this session. What is the motivation of this session? So here we are in the Royal Academy of Engineering, who is a representation of relevant engineers from the different disciplines of engineering in our country, in Spain. And we always try to look what is new coming, what is going to affect engineering, what is going to affect science, etc. And obviously, in the last years, 10 years, I think the amount of interest around quantum computing has increased a lot. Okay? And many of the members of the Academy were asking, hey, what implication may this have for our engineering in the future? We want to understand. And we said, okay, so we are going to organize this session so that we all become a little bit more familiar with this technology. I had to go back probably to my times in Caltech, when Richard Feynman wrote the famous paper in the International Journal of Theoretical Physics about simulating physics with computers, okay, who was probably the first person that postulated the idea of building quantum computers for simulated nature. This is already 40 years ago. And in these 40 years, I have to say that when the idea was put on the table, all the theoretical people in physics and in mathematics and in computer science start developing what can we do if we have a computer like this? So, and has been a tremendous development in terms of algorithms, information science, about qubit, etc. during these 40 years. But it's only in the last 10 years we have been able to start building one computer. So until then it was like, if the computer exists, we could be doing these things. But now we can say, hey, maybe now we are able to build a computer and we are going to realize all those things. And I guess this is one of the reasons that has increased the interest in the last decade about quantum computing. which is becoming now a broad area of focus, I would say, in all aspects of science and even society, I would say, not only in the scientific community. Now, as I said at the beginning, the reason we are here is because as engineers representing the different disciplines in the Royal Academy of Engineering, we want to know what implication this can have in civil engineering or in electronics or, I don't know, in agricultural engineering or in any other disciplines of engineering. And that was the motivation. And we have been very, very lucky, and it's an honor, a pleasure to have three very relevant people, professionals that are having a big impact on the development of all these technologies. Let me introduce the three presenters that are here with us today in the order in which they are going to speak and contribute to our session. Let me start with Juan Ignacio Cirac, which is the director of Theory Division in Max Planck Institute of Quantum Optics, where he has been in the job for now 21 years in Max Planck, which is great. He was born in Spain, in Manresa, and he graduated from the Complutense University of Madrid, where he also got his PhD in 1991 in theoretical physics. From there, he moved to several universities to land finally in Max Planck, where he has developed mainly his career, focused mainly in quantum theory of information, talking about applications, also the development of tensor networks, etc. And he has done a very significant impact in all these areas. I could spend here many minutes saying all the honors he got on his career and the memberships in the Academy of Science of Spain, Germany, the Bavarian, his corresponding members in the Austrian Zaragoza and Barcelona Academy, his fellow American Physical Society, etc., etc. But I guess it's much more interesting to listen to him than to listen to me saying what he has done. And he's going to talk us about quantum computing and the second quantum revolution. So that's going to be the first part of our session. It's about this idea of the theory, where this comes, what is the physics, all these kind of things. And from there, we move to the second presenter, which is Dario Hill, okay? He's very well-known member because he's my friend, okay? A personal friend. So Dario is the senior vice president in IBM and is the director of research, okay? He and I have worked many years in IBM together, and we have always a very interesting interaction, and we continue doing this today. He has the pleasure to lead an organization of more than 3,000 scientists, okay? And that work in developing the future for artificial intelligence, hybrid cloud, quantum computing, and other disciplines. He's also a member of the National Board of the United States of Science. Also, he's advisor to the Dean of the School of Engineering of MIT, and also member of the Academy of Science of New York. Dario got his PhD degree in MIT in electrical and computer science engineering. Okay, and he's going to talk us about the building of the machine. Okay, how is the future? What can we expect for the engineering in building a quantum system, and how this is going to impact or not the different disciplines of engineering. And finally, we have also the pleasure to have with us a good friend of Cesar Dopazos, which is Dr. Payman Gibbit. He is a distinguished professor and is the James Maclot Professor of Mechanical Engineering and Petroleum Engineering at the University of Pittsburgh. He has been before in the University of Buffalo, and he got the PhD from the Carnegie Mellon University. And what he's working is in the applications. We have all this quantum theory, and we have the machine. What things we could do with that in some area of interest. And in particular, because of his background, he did this around fluid mechanics and combustion. And because fluid mechanics was also my original area of science, so it was a perfect match for me when we put the three of you together, okay, with the concept of the theory, information theory, with the capability of building machine, and also talking a little bit about applications. So we are gonna listen from the three leaders, and later we open a session for conversation. Okay, I'm sure that people that is listening and following this session through our channel, our YouTube channel on the Royal Academy of Engineering, will be very glad to ask you questions. Right? What's coming? What's going to happen? What can we do with this? Okay. So having said that, I think that we can move ahead, and I will invite Professor Ignacio Cirac to start sharing his ideas with us.
Are you getting the questions?
No, no questions.
Who's getting the questions? Tú, las preguntas tú.
Okay, can you see my presentation?
Yes, we can see you.
Okay, great. Okay, well, let me first start by thanking the organizers, and in particular the Real Academy of Engineering of Spain, for this very kind invitation. And so I'm going to talk about quantum computation and the second quantum revolution. So this is going to be a very introductory talk, so I have to apologize to the experts that may be on the audience because of this very basic presentation. Anyway, let me start with something that appeared about 8 years ago in the cover page of Time magazine. So they were talking about the quantum computing. They call it the infinite machine. And it said in the cover page, it promises to solve some of humanity's most complex problems. It's backed by Jeff Bezos, NASA, and CIA. Each one costs $10 million and operates at 459 degrees below zero. And so they were talking about this quantum machine that I don't know if it was at the time in the mind of Jeff Bezos or NASA or something else. I don't know where they got these names from, or even if it cost $10 million. And but what they say at the end is very funny, because they say something, nobody knows how it actually works. And so it sounds to be something very mysterious, but in fact, it's nothing mysterious. I think that we know very well how it works. And so this is what I want to present here. And I think that my colleagues will also do here. And so in particular, what I want to show here is what is a quantum computer. So what can it do? And when will we have one? And of course, there are many points which are not clear yet, and then there will be discussion. There are different points of view. So I want to present here my point of view, which is coming more from the science side of quantum computation. Anyway, so we want to know about quantum computing, then we have to know a little bit about quantum physics and computing. And quantum physics, actually, it's a very old theory. Actually, it's more than 100 years old. So it started with Max Planck, who at the beginning of last century, said that in order to explain some behaviors in nature, it was required to quantize the energy of light. It's something that crashed against most common sense, because at that time people thought that light was made out of electromagnetic waves and that behave like waves. However, he was saying that not, we have to change the wording, and now we have to use photons. Actually, during the 2030s, so people, realized that that theory was explaining many experiments and many things that they didn't know before. But what was important, they developed a theory that was able to now explain everything that is surrounding us. So from the smallest parts of our world, from atoms, molecules, solids, liquids, gases, everything, and to a degree that was completely amazing. So nowadays it is possible to make a prediction of an experiment with 14 significant digits, do experiments and have that result. So one can say, if I measure that quantity, the result should be 1.0045. So with 15 digits, and whenever they do the experiment, which of course is very hard to get that many digits, then they see that it's like that. So quantum mechanics is not only a theory that explains, is a theory that predicts, and it's a theory that is very precise. Actually, it's the most precise theory that we ever had by far. And also quantum physics is part of our world. So we don't realize, but electronics is based on quantum physics. Lasers are based on quantum physics. Many of the equipments that are in our hospitals are based on quantum physics. So people say that 35% of our economy is based on quantum physics. So it's something that is surrounding us. So what is new then about quantum computing? Well, quantum computing actually, it's using some other laws of physics that are a bit more exotic, and they are not exploited in current apparatus. So maybe some of you have heard that when quantum physics was developing, some of the pioneers like Albert Einstein and Niels Bohr started questioning the theory because it had some very strong implications about nature. So in particular, there are sentences by Einstein that were saying that he doesn't play dice, meaning that it cannot be that nature is so exotic as quantum physics. And this is because quantum physics, apart from all the predictions that make current computers and electronics possible, has some of the principles which are more weird and that tell us that in the microscopic world, so whenever we go to these very, very small things at the level of atoms, molecules, and that level, then I mean, reality is a bit funny. So first of all, the properties of objects are not defined or are not necessarily defined. We don't observe. So taking it, exaggerating that, that's what Schrödinger was saying. So whenever I don't look, is the moon there? Of course it's there. I mean, I don't know where it is, but it's there, it's somewhere. However, quantum physics goes beyond and says that whenever we go to the microscopic world and we say, is an atom there? Actually, it's not there. So it has not defined its position. It's only when we observe that we define the position, and it happens in a random way. And this is why Einstein didn't like that nature somehow it's not defined, and it's we as observers that define physics. In any case, this I mean raised the attention of philosophers and physicists and physicists, and came, I mean, some of them came up to some kind of extraordinary situation. So what will happen if this, what happened in the macroscopic world will also happen in our world? Then it should be possible to have a macroscopic object like a cat that has not defined its property yet. So it's at the same time life and death. And this gave rise to the paradox of Schrödinger cat, in which if whatever happens in the microscopic world would also happen in our world, then it should be possible to have a cat that is at the same time alive and dead. And only when we look at it, then it's dead or alive. So it's, this property is defined. Now, after many years of discussions, about 30, 40 years ago, people were able to do experiments. So technology progressed so much that it was possible to do experiments with single atoms, with single objects, and really make sure that in this kind of indefiniteness of quantum physics is like that. And in fact, nowadays, we can have, for example, a single atom with a property, and this property could be what we call a spin. And this is nothing else but, I mean, based on the fact that an atom is a small magnet. And spin tells whether the magnet is pointing up or pointing down, for example. And so according to quantum physics, if it's possible to have an atom with a magnet, with a spin pointing up, and it is also possible to have it pointing down, then we don't observe it. It should be possible to have it in the superposition of both of them, or what is the same, to have both situations at the same time, in such a way that only when we observe this property is defined. This can also happen with superconductors. So if it's possible to have a very, very small circuit, and it's possible to have current that is moving clockwise, and also it's possible to have current moving counterclockwise, then according to the rules of quantum physics, it should be possible to have a superposition, namely both of them at the same time, in such a way that the current has not decided where it's going, and only when we observe that's when it's defined. So that's what we call in quantum physics superpositions. That, let me make it very strong statement, it occurs in our microscopic world, but it cannot be extrapolated to the macroscopic world, and we understand very well why this cannot happen. But anyway, in quantum physics, then we represent these situations with a language, which is the language of quantum physics. So we assign to one of the values of the property, for example, spin down the value 0, to spin up the value 1, like a bit of information. And according to quantum physics, we can have both at the same time, which we write in this form, and we call it a superposition. And a bit that can be in a superposition, a bit that obeys the rules of quantum physics, whose state is not 0 or 1, but can be anything in between, or both of them at the same time, is called quantum bit or qubit. Now the situation gets more interesting if we have many of these quantum bits. If we have, for example, many atoms, we can have the order of 50 atoms, we can have 50 or 100 of these superconducting circuits. And now if you assign again a quantum bit, a qubit, to each of these objects, to each of these atoms, then we can have each configuration, and not only each configuration, but a superposition of all possible configurations. So we can have that all the atoms are spin down. So this would be the state that we'll call 0, 0, 0, 0, 0, 0. Or we can have the state in which only the last atom has spin up. This would be 0, 0, 0, 0, 0, 1, or 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1. And if you count how many configurations we have 2 to the power n, where n is the number of atoms. So we have an explosion of superpositions. So we have an exponential number of configurations, an exponential number of potentialities that are at the same time and that are occurring at the same time. And only when we observe, when we measure, then this state is defined, and one of the superpositions survives. Now, this, apart from being already checked in many laboratories, the existence of the superpositions, the properties of the superposition, something that does not occur in our microscopic world, then people realized already many years ago that can be used to compute. And roughly speaking, so if we have many superpositions, many configurations at that time, then we can do a computation in parallel with each of these configurations. We can do a different computation. So they are living, let's say, all the same at the same time. They are not defined, and only when we measure, then they will be defined. So that's what Feynman called quantum parallelism, which meant that with a single, let's say, set of quantum bits, we can do many computations in parallel. Just to give you a number, if we have 300 qubits, then the number of configuration is 2 to the power 300, which is basically 10 to the power 80. That is the number of atoms that we have in the universe. So if we would like to, simulate these superpositions now with a classical computer, with a standard computer, then we would need a computer of the size of the whole universe just to represent whatever we can do with these 300 qubits. So this shows this power of quantum computation, namely that the fact that we have the superpositions makes something possible that otherwise would be completely impossible. However, one has to warn that, this is not exactly true, because these superpositions that exist at the same time, one can do computations in parallel, but whenever we measure, then only one of them survives. So all the other ones will disappear, and therefore we lost all the advantage. So this is why in quantum computation is not only about having superposition, but also interference. So we have to make sure that we use the superpositions to solve a problem, but at the end, when we measure, that we got the right result and not a random result. And that's the art of quantum computation. So now I can define what a quantum computer is. A quantum computer is just a device that in which you can give an input, it will give you some output, and there will be some process in between. This process, instead of using bits, this process of information, instead of using bits, you use qubits. The qubits are set in superpositions, and at the end we measure. So that's what is represented here. So that's a timeline going from left to right, in which you have the qubits all starting in the state 0. Now, depending on the problem that you want to solve, then you will apply some quantum gates. So these are like the gates that occur between bits, but these are quantum, meaning that they can create superpositions. And if you have a sequence of gates, then you will create superpositions, many superpositions. And at the end, if you are a good programmer, then you will have to have some gates in such a way that these superpositions basically disappear, and then you have only your solution at the end, so that when you measure, you solve the problem that you want to solve. So with this, I want to illustrate a basic fact that I think that is very important for quantum computation. So quantum computation indeed harnesses superposition, uses these laws of quantum physics to do something that is completely impossible with classical computer. And this, as we know, can solve certain problems more efficiently. And I here say certain, because it's not that all the problems you can exploit the superposition, it's only the ones in which you can make sure that you create the superpositions, and then at the end, you just have the right result. So you use the superpositions in the middle of the computation, but not so much at the beginning, at the end. Okay, and that's what people have called the second quantum revolution, because first, one changes the classical computation by quantum computation. That's a new way of doing computation, and people compare it to the change that was done when computation were done in terms of abacus to electronics. Now from electronics, you go to quantum physics, and this is a change of paradigm, which can have a lot of advantages, can solve certain problems much more efficiently than we will be able to do with a classical computer. And since there was already a quantum revolution which gave rise to electronics and so on that I mentioned before, this is called the second quantum revolution, in which these other laws of physics are exploited. So what is the state of the art? I think that we will hear more about that later on. So do we have a quantum computer? So actually there are many platforms in which people are building quantum computers. The most advanced are the ones based on trapped ions. So there, what people do is that they take neutral atoms, they ionize it in such a way that they are ions. They put some electrodes in such a way that these ions now are levitated, and you store one of the qubits in one of each of these ions, in the spin of one of these ions. And now by manipulating with lasers, then we can create these quantum gates, the superpositions, and run the quantum algorithms. Another technology, I think that Dario will talk about that, is based on superconducting devices, in which one uses these small superconducting circuits and as qubits and connects them with circuits, and then one can build many of such qubits. So the advantage of the first is the precision, that's very precise. However, scaling is more difficult, whereas the second one, maybe it's more difficult to get precise quantum computers, but it's easier to grow. Now, this is a race between different technologies. That's the most advanced at the moment, but there are other technologies that are coming up. So for example, 3 weeks ago, so people have another technology that's based on Rydberg atoms, and they were able to have 260 Rydberg atoms with a kind of very good, what we call fidelities, and run some algorithms with them. Then there are some other technology based on photons in which they are doing some progress. So I don't think that the final technology platform in which quantum computers will be built has already been found. Maybe one of those, the ones that we have here on this transparency, or maybe another one, but that's the state of the art, of the order of 50 to 100 qubits of these qubits running in quantum algorithms. Now, the problem why it's very difficult to scale them up is because they require very extreme conditions. So trapped ions have to be in vacuum. If there is a molecule coming by and crashing against one of the ions, it will destroy this state, will destroy these superpositions, and then the computation will be gone. The superconducting qubits have to work at very low temperatures. The cold atoms have to work also on extreme vacuum conditions. So that's why, I mean, it's very difficult in practice to create this kind of quantum computers. And so in all these computers that we have so far, there are errors. So this means that they don't operate ideally. So some of the qubits during the computation, I mean, get wrong, and actually the superposition in that qubit is erased. And that's why there are two options that people are now pursuing to build quantum computers. So the first one is to cope with the errors and to use noisy devices. So despite the fact that these quantum computers are not perfect, there will be errors, they may still have some advantage to some particular problems. And these kind of quantum computers are called noise intermediate scale quantum computer, NISQ devices. And there is a lot of effort to build these devices, to make them bigger, to have less errors, and also to find applications, as I will mention later on. The second option is to correct the errors. So there is a possibility of correcting the errors. So people familiar with information theory, with classical information theory, they know that, you know that when there is some error in when you're processing or transmitting information, there are ways using redundant coding of correcting the errors. The question is that in that case, you have to have some overhead. So for each bit of information that you want to code, you need a number of physical bits that will encode this information. So you have to multiply the requirements in the number of bits by some number. And the same thing happens with quantum computers. You want to build a quantum computer that has errors and make one that doesn't have errors, then you will have to build many more qubits than originally decided, because of this redundancy that is required to correct the errors. Now, that's a little bit of a time scale of quantum computation, because there was the origin by Richard Feynman in 1981. There were some theoretical works, but from the point of view of implementations, so the first quantum computation, I think, that goes back to 1996, where it was done, people did some computation with 2 qubits. At the time, this was from an ion. And then later on, this was progressing a lot, so people were able to reach something like 10 qubits or something like that. In around 2012, the industry came to help the scientists, and then there was a very big, very important progress in the field. And then IBM was working before, but IBM, Google, and some other companies, pushed a lot the field. And in 1919, there was this, what is called Supremacy Experiment, in which it was possible to build one of these NISQ devices, this error, a quantum computer with errors of 53 qubits, but was good enough such that it was able to do a computation that would take very long with a classical supercomputer. And now later on, this was improved. So some Chinese colleagues did some other experiments with more qubits. And so at the moment, there is an academic problem for which we know that a quantum computer can solve it, but we cannot solve it with classical devices. It would take too long for that. So now, then basically at the time we entered this NISQ area, in which the goal is to develop this NISQ to have, I mean, some devices of the order of 1,000, maybe 10,000 qubits that will have little errors, but still that in the presence of errors have certain applications. So in a sense, we are now like, I mean, people were in the 40s where the first classical computers were built, that they're very big devices, difficult to scale up, and that, I mean, they don't have that many applications. And we hope that in the long run, so people talk about 10 years, 15 years, 20 years, 30 years, we will have these error-free devices, scalable, in which we will have all the possible applications. So summarizing, we just have entered this NISQ area where we have these very interesting devices that are a little bit noisy, but still they can do some things that we cannot do with classical devices. And now the research there is, what can we do with these devices? And for a full-fledged quantum computer, we'll have to wait some time because it's very difficult to scale due to the problem that I mentioned with the errors. Okay, and so last, very briefly, let me talk about applications, but I think that my colleagues will tell you about some other applications. So there are many applications, and one can classify them in different ways. So one way that I like to classify them is in the one that you see here. So there are applications for quantum computation for specific problems. So for example, we know that quantum computers can factor numbers very efficiently, or can take discrete logarithms very efficiently. So we had a quantum computer, we could factor a 1 million digit number very easily. And that's a particular problem. And it turns out that this problem has a lot of implications, because current cryptographic systems like RSA are based on the difficulty of factoring numbers. So if we had a quantum computer, this would mean that current cryptographic methods would not be secure anymore. Now, in the same way, there's some other problem, Bell's equation, and some kind of looking in some graphs and so on, which we know that quantum computers are very efficient, much more efficient than classical computers. There is this other set of problems which are related to optimization. Optimization is something that it's used everywhere in the industry, but also in science, in everyday's life. And so many problems can be translated as an optimization problem. And that's what it gives quantum computation, like say, a broad potential, beyond solving some specific problems. So a typical optimization problem, for example, is a traveling salesman. So somebody gives me some cities, and then I have to find what is the shortest path that goes through all these cities. This is a combinatorial problem, and the number of possibilities explodes. So by going through all the possibilities is basically impossible when we have something like 30 cities. However, a quantum computer can accelerate that problem. However, one has to say that the acceleration of quantum computers in optimization is not as big as it is on the other problems that we know. So it's what we call a polynomial acceleration. So it's, I mean, of course, we will have practical uses, but it's not at the level of some other accelerations that we can get for quantum computing. Now, another area is in data analysis. So people have figured out how one can process data and use in particular in machine learning. And so there are some results that indicate that quantum computers can be very useful in machine learning. Some of them are speculative, but I think that there are some solid results already in that field. And the last one, I think that it's one that's very important, is in simulation. So it turns out that if you have a problem in chemistry, in pharmacy, in material science, and so on, if the object that you want to make a predictions, or you want to exploit, or you want to produce, obeys the laws of quantum physics, then it's very hard to describe with classical computers. The reason is very simple. So it's a quantum object, it's a quantum object, and it's made out of smaller objects. So the physical properties will depend on superpositions. And since there will be so many configurations, then there will be many superpositions, and this exponential number of superpositions is something that we cannot cope with classical computers. And this is why quantum computers are very handy there, because now you want to simulate a system with 30 qubits, just use 30 qubits, don't use a classical computer with 2 to the power 30 bits of information. That's actually the application that Richard Feynman was the first who was paying attention to. And this has consequences in chemistry, where if you want to study reactions, or you want to improve reactions, or you want to optimize reactions, or you want to know what is the configuration of a molecule, or in material science, when you want to design certain properties of materials, or even in more scientific research, like in high energy physics, then it turns out that there are many, many problems that if we had a quantum computer could benefit from them, because here there is again an exponential speed up. So there will be computation that we will never be able to do with classical supercomputers, that if we had a quantum computer, we will be able to do it. Now, so what are the requirements for these problems? So you see, we had an error-free quantum computer, a scalable quantum computer, and you want to solve a problem like the factoring problem faster than with any classical device, then you will need of the order of 10 to the 3 to 10 to the 4 qubits, and of the order of 10 to the 8 to 10 to the 10 quantum gates. But since you have errors, even if the error per gate is of the order, the probability of error per gate is 10 to the minus 3 to 10 to the minus 4, then you will have to use this redundancy. And this redundancy means that the number of qubits that you will need will have to be multiplied by 1,000 or 10,000 with these numbers. You will require of the order of 10 to the 6 to 10 to the 8 physical qubits, and of the order of 10 to the 13 to 10 to the 17 quantum gates. Now, that's apart from that, I mean, there are some requirements for fault-tolerant error correction. One of them is that the error per gate in your quantum computer should be independent of the size. So you do an experiment with 20 qubits and you put 2 million, then still the error should be the same. It's hard to fulfill in practice, and also has to be fully parallelizable. So you have to act on all the qubits at the same time in order to do these gates. Now, what is expected, and if we talk to our colleagues here that are building these quantum computers, then some of them say that in the next 3 to 5 years, they will have of the order of 10 to the 3 to 10 to the 4 qubits. The errors per gate are between 10 to the minus 3 and 10 to the minus 4. And so this means that without errors, then they will be able to do of the order of 10 to the 2 to 10 to the 3 gates. So this means that most of the problems that we know that the quantum computer can solve, I mean, cannot be solved, let's say, in the next 3 or 4, 5 years. That's why there is a lot of attention in what other problems can we solve with these quantum computers that are coming, these mixed devices, these ones that have errors, and that could give some advantage and have some practical applications. And it seems that the simulating material, simulating chemical problems is probably the one that has more chances of have, let's say, industrial applications. I'm sure that my colleagues will talk about that, maybe with a different perspective. But anyway, so that's what I just wanted to give you a summary of what a perspective on quantum computation, so what it is, so what we expect to do with these quantum computers, and also what we can do right now, and what we expect to do in the next 3 to 5 years. So in summary, in the long run, quantum computers will have a big impact. So we know that they can solve some problems that are of practical use and that will be impossible to solve with classical computers. But meanwhile, in the short run, so we can probably find some specific applications. And probably one of the biggest hope for these applications in the world of many-body quantum systems, in the world of material science, physics, chemistry, drug design, and so on. In any case, quantum computing is experiencing a very exciting moment, because it's not only done in the labs, it's also the industry are pushing for that. The governments are very interested in that, and the German government here has approved $2 billion for the next 5 years on quantum computation. So it's a lot of funding going on. However, I also want to finish saying that we have to be very cautious. So we don't have a full-fledged quantum computer, and it may take a long time until we have it. And with that, I would like to finish, and thank you for your attention.
Ignacio, thank you. Thank you very much. It was very, very interesting. We are going to move now to Dario, and then we'll have the conversation. Okay, so Dario, now is your turn. Show how many qubits we are going to have in the next years.
Okay, well, thank you. And as Ignacio was saying, it's really a wonderful pleasure to be invited and to be with all of you, and also to share the virtual stage with such esteemed colleagues. So wonderful to be with all of you. So let me see if I can share this. Back to this. Okay, here you go. Okay. So first, by since we're virtual, by means of introduction, this is where I'm speaking to you from. Is the headquarters of Ibm Research. It's about 45 minutes north of New York City. And as Juan was alluding before, is this beautiful building that was designed by Eero Saarinen, And of course, we have a global network of scientists in IBM Research. But a lot of the activities I'm going to talk to you about in the progress of quantum computing takes place in this building, although not exclusively. But I thought it might be useful to have a, geographical, ubication of it. Okay, so Ignacio has shared like a very nice overview of why quantum is different than classical computation. I just want to highlight the fact that we should not view quantum computing as just another step on Moore's law or just a natural evolution of computing, but that we're experiencing the first time where the category of computing with a capital C is branching. And of course, we will continue to push semiconductor technology, the way we process our regular bits and making them cheaper and more efficient, but that we're in this unique moment where moving forward, we will refer to as all the computers we've ever built as classical computers, and then we will have this new category called quantum computing. So it's quite fundamental, and it doesn't happen quite often. Obviously, it has been built over many decades, both the theory, what is known as quantum information theory, as well as the technology that is beginning to allow us to build these quantum computers. But that's the first point. It's not just a faster classical computer, but something that is fundamentally different around that. And in fact, the historical analogy, perhaps it can be somewhat similar to what happened in the 1940s and the 1950s. And where, until very recently, the example of what, running a program looked like, it looked like something on the left. I mean, you're seeing a picture here of Jerry Chow in 2015 in one of our labs, where you would have all these, room temperature control electronics that would send these pulses into these experimental devices. And that was the basis in which people were doing like, very, very basic and simple qubit computation. I think an important moment and a significant inflection in the commercial field for sure, but I would argue also in the way the community is being exposed to quantum computing, happened on May 2016 when we put the first small quantum computer, which just had 5 qubits, on the cloud. And basically, instead of having to be the equivalent of Jerry Chow tweaking, those pulses, you could just sit in front of a computer, and you see here like what the interface that we created looked like. And remember that Ignacio showed you those circuits with those lines that had quantum gates. So you're seeing here reflected, and you could just simply drag and drop those gates into the interface, and you could click run, and it would run on an actual quantum computer. I'll show you how it goes, and I'll show you the implications around that. In our case, the system that we built was based on superconducting technology. Ignacio mentioned that there's different ways to build a quantum computer. In IBM, we use a device called the Transmon qubit, and it works at cryogenic temperatures, about 15 millikelvin. You're seeing here what the inside of one of our quantum computers look like. You see this kind of like golden-like chandelier. And I'm going to show you a little animation of that, where you have these superconducting coaxial cables that allows us to send energy into the system. And in the end, at the bottom, you see that shiny little square at the bottom. That is a quantum processor itself that incorporates the qubits, and that allows us to perform the quantum computation. So what we built at the time was the following. You could sit in front of your laptop anywhere in the world, and you would write a little program, and you would send the zeros and ones over the internet. It would get to our quantum computer, and we would convert it to microwave pulses that operate about 5 gigahertz. The pulses would travel down the cryogenic refrigerator. Eventually, it would get down to the quantum processor, and we would generate the superposition, entanglement, and interference operations that are the characteristic of a quantum circuit. At the end, we would perform a measurement. We would amplify that measurement up through the cryostat and convert that pulse that you get out into zeros and ones, and we would return the answer to the user. So we did all of that, and that all sort of happened, stably and day after day, 24/7. And what happened is that we saw the emergence of a quantum community. So now, beyond experimental laboratories that had access to kind of these quantum devices, all of a sudden anybody with an internet connection could start doing their simple programs on a quantum device. And what you're seeing here is the community of users since May 2016 that have been running experiments in using IBM's quantum hardware. So you're seeing here, we gave access to both simulators and actual quantum devices. And what you're seeing is that today, 1.8 trillion of American style, 1.8 billion in Spain, circuits have been executed using IBM quantum hardware. So this is now something that happens routine. In fact, every day, 3 billion quantum circuits get run on IBM quantum hardware, just to give you a sense of the scale of operations. And we have over 20 quantum systems online that our community uses. As a consequence of this progress too, institutions all over the world have joined our quantum network, and you're seeing here a list of everything from Fortune 500 companies to national laboratories, universities, startups. When you look at it, all in all, over 180 institutions worldwide are part of this network. That is something that continues to grow very significantly. And in fact, not only have we built these kinds of systems that we have in New York, as I mentioned, over 20 of them that are online, we've also begun fielding these early quantum computers across different geographies, right? So in fact, we put one in Germany, in Fraunhofer. There's one operational at the University of Tokyo. We will deploy one in the Cleveland Clinic, in Korea, in Quebec, and many more to come. So this is something that is beginning also as a scientific and engineering tool for education and research and industrial exploration. I think one of the exciting things that is happening is that the next generation of scientists is extremely interested and excited around learning this field and contributed to this field. We have created lots of tools and education and certification programs online. And to give you also a flavor for this, in terms of our open source environment, over 3 million learners access these digital tools that learn about classes on Qiskit, which is the most widely used open source software kit to develop and explore quantum computing tools. There's over 50 research and educational partners that are creating specialized curriculums on quantum information and quantum computing. 12 of our systems, we enable them and provide free and open access to these universities and the community. And then there's massive interest in terms of students, in terms of furthering their education and professional experience. To give you a sense, every year, we have about 60 summer interns that come to IBM Quantum. And, in the last couple of years, we've received more than 15,000 applications for those 60 slots. To give you a sense of just how much enthusiasm that there is in the community. As Ignacio mentioned, there is a set of class of problems. I wanted to touch briefly on what are the kinds of things that the community is exploring, and then I'll tell you about the state of the hardware and the systems. We like to divide them into these three buckets. There are categories that, once we have sufficiently large and advanced quantum computers, they will deliver, exponential speedups. Of course, one category is the simulation of nature that obviously obeys the laws of quantum mechanics, and you can have a good mapping between the nature of those problems and the quantum computers that we're building. So these will matter greatly for problems in relation to physics and chemistry and material science. There's also problems that are of great importance that have to do with data that has structure within it. The problem of factoring that Ignacio alluded to is a good example, but there are others in terms of ranking in groups and machine learning applications. That is a burgeoning new field. And then there's classes of problems. Quantum computers are also universal computers, and there are problems for which they will deliver no advantage at all. There are many of those compared to classical machines, but there's also will be problems where you get a non-exponential speedup. Ignacio alluded to polynomial speedup, and that's an example of some sampling and search problems, optimization, and others. So the objective is to, across these different categories, to deliver quantum advantage, which will be the stage where a quantum computer can solve problems that are either cheaper or faster or more accurately that you can do with a classical computing. And there's lots of institutions, both in academia and startups and major companies, that are beginning to explore what use cases might these be, beginning to educate and train their teams around how to think in this sort of new world of quantum computers, and develop the skills and start developing, and publishing and developing the intellectual property and knowledge to take advantage of this new category. And I just give some examples here, and be happy to send also the reference to the published work around this. But everything from major financial institutions like Goldman Sachs that are exploring, how this could be used to price complex derivatives, to energy companies like Woodside that are applying it with some of this new area around quantum machine learning to improve predictions, to Boeing, who is using it for problems related and exploration or optimization of the arrangement of fibers for composite materials to build critical components in aircraft. Boeing is also pursuing a project collaboratively with us on the topic of corrosion. Daimler, also in connection to some of these advances around a project around battery materials. And you see other examples here with Exxon in terms of calculating thermodynamic observables for next generation energy solutions. So all of these have, like I said, happy to send some reference papers around it. In fact, one way to look at it is that, just like other instruments, is becoming a scientific tool, these quantum computers. And I'm showing you a couple of statistics here. On the left-hand side is the number of journal papers that have been published since May 2016 using IBM quantum systems. And you're seeing here these dramatic growth where over 1,500 papers now have leveraged this as a scientific instrument to do research, right? To explore interesting new ideas. In the major conference with a lot of quantum work takes place in the American Physical Society meeting, APS, March meeting. You see also here very significant number of papers that use this as a tool, right, to advance the state of the art of research. And I include below some examples of demonstrations and exploration about quantum information science that was simply not possible to do if these systems were not available. And in fact, I include here, I don't mean to read all of this, but there are many, many examples of how this is being used for advancing science and sort of leveraging increasingly capable quantum information systems and quantum computers. So what's next, and how will we be able to achieve quantum advantage in the near term? So some guideline about in the design of algorithms to exploit this technology is we need to be able to focus on classes of problems where we have a path to deliver either super polynomial or exponential quantum speedup, right? We might make sure that we pick problems that are well suited for quantum computers, and we don't pick problems that are well suited for classical computers to do very well, right? And very often, many people do demonstrations of things that this, even though you can run it on a quantum computer, you really don't have a path, even if you have bigger machines and better machines, to demonstrate that kind of advances and exponential. So picking the problem matters a lot. To be sophisticated and clever around using even heuristic versions of the algorithms. And I think there's going to be sort of a practicality and a heuristic determination of progress that will be very important, and to be clever about that. To be well adapted to the reality of where the quantum systems are. So adapting those circuits for the kinds of systems that we have will pay a lot of dividends. And well before we have full error correction, we are going to exploit error suppression and error mitigation if you know how to characterize the systems well to be able to deliver quantum advantage. So to do that, we are going to have to make sure that we have systems that can improve, and I'm going to tell you about that. And we need to have software that seamlessly integrates quantum and classical computation. So the future is not just quantum, it's classical and quantum working collaboratively and working together to extract the most out of the noisy devices that we have right now. So I want to tell you where is the state of the art right now and where are we going over the coming years. Last year, we released the IBM Quantum Development Roadmap. And this is something that is quite exciting because it gives you a set of milestones that we're going to be delivering over the coming years. And the way you read this roadmap, and I'll unpack it in a minute, is at the bottom, you see the system itself. Think about it as the hardware modularity. So the first system that we put online, remember I told you it had 5 qubits. We have since delivered many generations, 27 qubits, 65 qubits. Last year, we were the first company in the world to build a 127 qubit superconducting system. This year, we will deliver 433. Next year, 1,121. And I'll show you that we have a path to scale to many thousands and tens of thousands of qubits over the coming years. But above it, and incredibly important to make this is not a story just of the hardware, the story of the software, the algorithms, and the hardware all working together. So there's a stack, everything from kernel developers. In the classical world, think about them as assembly language, right? Low-level programming that allows you to incorporate the noise present in the systems and deal with that. And how do you actually control the pulses that control the circuits, etc. Above it, algorithm developers, they also have to know quantum physics to do that. But this is where you develop algorithms like quantum machine learning as an example, right? And above it are model developers. Now, this community will not need to know anything about quantum physics. They just need to know that there are quantum libraries and they can incorporate those models into their software applications. And that vision is where we can expand the field tremendously because it'll be the equivalent of just calling functions or libraries and taking advantage of it in your favorite programming language without having to know anything about quantum physics. So increasing the level of abstraction will be very important to develop and expand the range of the field. So next year will be a very important year because a lot of the things are going to come together to expand the field. And let me unpack it very briefly around 3 vectors that are going to be crucial for progress: scale, quality, and speed of these quantum systems. So for scale, is going to be linked to how big a problem we can solve. And to do that, we have to build larger and larger systems. Now, creating larger systems require improvements on the device itself. So in our case, the transmon qubit and the precision with which we can build the junctions. How do we do scalable measurement of this exquisitely delicate set of quantum information? How do you package the processor technology? How do you do scalable I/O in terms of sending signals and wires that come in and out of the system? Building a system is much, much beyond building a device. Many, many things have to come together and is one of the things that sometimes can be underappreciated, the scale of it. I mentioned that last year we were the first to break the 100 qubit barrier on superconducting technology. We're very proud of this technology because it's the first time we've broken the plane, and we have now created fully integrated 3-dimensional quantum processors where you go from the qubit junctions that are on the bottom of the stack, and then the interconnects between the qubits and the signal processing, et cetera, now happens on a multi-layer wiring that incorporates through silicon via superconducting technology, and is quite an achievement in terms of packaging technology. And it allows us to very significantly increase the modularity of these systems. In fact, the way we're going to build systems with thousands and tens of thousands of qubits will be to build processors with a very large number of devices, let's say about 1,000 plus qubits. And then we're going to start parallelizing them. The first generation will enable parallelization between multiple quantum processors using classical communication. Now that is exponentially costly from a classical computing perspective, but nonetheless, we can make advances in that direction. The next generation after that, in 2024, we will start establishing quantum communication links between quantum processors that are right next to each other. These will be extremely high fidelity and very fast gates. And beyond that, we're also going to demonstrate quantum communications with larger link nodes. In this case, it may be as big as a meter-long quantum communication channels that will be lower in quality, but nonetheless, allows us to have quantum entanglement across processors that are, in different refrigeration units in the cryostat. So if you combine all of this together, large number of qubits per processor, many processors combined together in terms of like quantum links and longer links, we are going to allow us to build machines that are going to have thousands and tens of thousands of qubits in the near future. I want to touch next around quality. As Ignacio alluded to, we have the challenge of dealing with errors. And basically what we're asking here is, how coherent are our quantum devices? How much time do we have a qubit before the coupling with the external world makes it into a bit? Here is one of my favorite plots in quantum computing, and it's a plot of the progress we're making on building lower error rate superconducting devices. On the x-axis, you see years starting in 2017. And on the y-axis, you see the error rate. All of these are experimental results of quantum processors we have built. And what you're seeing here is just a few years ago, we would have about every 100 operations, we would have 1 or 2 errors. Today, last year, we demonstrated an experimental device for a superconducting device that has an error rate of 10 to the minus 3. So, every 1,000 operations, you get 1 error. And importantly, please note the progress we're making. There's a slope to this line. And you can sort of see that at the rate of progress we're going, in the next couple of years, we will demonstrate error rates that are 10 to the minus 4, 1 in 10,000 operations. And that combined with scale of devices with hundreds of qubits, combined with error mitigation and error suppression techniques, with the right problem set, likely in the area of materials, is likely to enable us to do the first demonstrations of quantum advantage. And lastly, I want to talk about speed. Speed is very fundamental. To solve any practical problem, you're going to have to run millions or billions of circuits sequentially, one after the other. And one of the things that we like about superconducting qubit technology is that it allows us to build very fast circuits. In fact, they're about 1,000 times faster than other technologies like ions. And that is one of the reasons why we're excited to build scalable, fast, high-quality systems for quantum computers. But in fact, the problem, it goes beyond having fast devices. You really have to take a systems approach and combine classical and quantum computation together. That's why we have spent a lot of time building the software called Qiskit Runtime that allows you to orchestrate from the original design of the program to be able to allow you to create the quantum circuits that are going to be executed, and then be able to, from there, to execute the program iteratively, where the quantum circuit gets generated, gets run on a classical machine, in a quantum machine, then it gets iterated back into a classical machine, and you go through this loop where there's a massive orchestration going on between classical and quantum computing to deliver you the results. Just remember that the calculations will involve millions and billions of circuits that need to run iteratively to get to the answer. So to close, one of the things we're going to do is to bring all of these things together, right? The higher quality devices, larger number of devices, all connected to one another. And just like we have seen in the past, the era of CPU-centric supercomputers, we've also seen the last decade of GPU and AI-centric supercomputers. I can assure you that we are going to see the era of quantum-centric supercomputers. And this is something we are working very hard on making a reality and developing. And this is we unveiled relatively recently what is known as IBM Quantum System 2, which will be the first quantum-centric data center. So you're seeing here the next generation of cryostats that are going to be able to house multi-thousand qubit devices inside it. The center is where the quantum processor sits. The periphery around that are the control electronics that are going to drive those quantum computers. But importantly, too, it's a vision of how we will have many of these quantum systems inside a data center environment. In a first generation, you will see classical communication and classical computation connecting multiple of these quantum systems. But over time, we will also engineer a quantum intranet, where the long-range coupling will enable also entanglement to happen between multiple quantum processors and quantum computers. And ultimately, in the decades to come, not only will you see quantum data centers, but you will see the interconnection between quantum computers over long distances on something that is known in the field as a quantum internet. So that gives you a flavor for how things are. What I would say, and I'll stop here, what I will say is that the field is progressing increasingly rapidly. There's so much to do. This is back to like the equivalent of the 1950s, as I was alluding to before. It's a beautiful field to be engaged and to attract lots of talent. And actually, in fact, some of the excitement is just the sheer amount of work to be done on this wonderful space. And just a final observation. I think one of the things that we are contributing to the field is that before, the field was very much centered around, ultimately, there will be a fault-tolerant quantum computer. And the framing of this was, that's the moonshot. Like, we should go work on this and eventually come with a fault-tolerant quantum computer. Our point of view is that, yes, that's the ultimate destination, but the journey is by iteratively building more and more advanced and capable computers. And that is how classical computing happened. The fact is, people didn't sit around and people say, oh, one day there will be like, the perfect classical computer. It began journey by journey, step by step, and it got more and more capable that it could do more and more and more. And that's our philosophy for how we do science and engineering on this. And hopefully you got that sense to see that the pace of progress is rapidly accelerating and a lot more to come. So thank you.
Dario, thank you very much. Very, very interesting. So we have learned a little bit of theory. We have seen what Dario is going to build for us. Sure. And now, Dr. Payman Kivit, you are going to tell us what are the things that you are trying to do with these devices.
All right. Hopefully you can see my screen okay now, correct?
Yes.
All right. Well, first of all, I really want to say that I'm very thankful to be invited by the Spain Royal Academy. It is an honor, especially it is my honor to be sharing this this symposium with Ignacio and my colleagues. Thank you so much for having me here. Well, I am in the Mechanical Engineering and Full Center for Research Computing. So by training, and I work on engineering and physics, and the stuff that we are working on are primarily on the applications or future applications of quantum computing in science and engineering. So first of all, this is where I am talking from Pittsburgh, one of the most beautiful cities in the universe, and the University of Pittsburgh, in my opinion, the best university in the universe. This is where we are located, and this is the downtown Pittsburgh. I would be glad to be hosting you if any of you guys want to visit or go to city. So, why am I doing this? In quantum computing, especially on the engineering side, there are a lot of myths and a lot of speculations, a lot of doubts, and a lot of too much of hope on what quantum computing can do and cannot do, and there are a lot of exaggerations, and at some point a lot of over promises. And I have been very lucky to be collaborating with a very fantastic group of theoretical physicists and quantum algorithm experts to try to with that, there's problems. What can be expected? What can we do? What are the things that are quantum ready, can be used right now on the quantum machines that are, being out there? And one of the things that algorithms or whatever that has been inspired by from the quantum world. So as what discussed in the previous lectures, and I won't go through them in details, the whole idea of quantum computing, something came in the 1980s. If you are in the US, they say it's Richard Feynman. However, if you are in the Eastern world, in Russia or others, they think that the first one was Yuri Gagarin who came up with the idea. But however, whoever the original idea came in, it was basically in the 1990s with the Shor and Grover algorithm that the field of quantum computing. So, as by Ignacio indicated, the whole business of quantum computing, the fact that you are working with qubits as opposed to bits in a classical computing, and this quantum advantage primarily are based on two properties. The first one being a superposition. Thing could be in the combinations of at the state of being zeros and ones. How could it be? Something like this. Things should be in the state of being 0 and 1. The first property, and the second one, the process of the entanglement. And the fact that, as Ignacio indicated in his talk, if you have like 1,000 qubits, you can have a state of something can be specified by 10 to the power of 300 coefficients. And this large number, has caused a lot of people to think that this is maybe overnatural or whatever, at least in engineering. For many of us who really do not have the fundamental knowledge of the physics of quantum computing. Now, the fact that quantum computers are being done by means of a lot of gate operations, it has some advantages or some disadvantages, and the primary advantage is that with all this unitary operation of the computers, you can realize the power of entanglement of those machines. And this is that power that it helps people to devise quantum algorithms that make things to go fast. So what the way that we would typically do in a classical computing, when we turn on the computer, we start doing the computations, and at the end, we read out the information, and that is where the end of the calculations are. And here at the end, whatever the result that we read, it could be either deterministic or probabilistic. That's what classical computing is. Now, on a quantum computing, when you start the kind of calculations, by the nature of the things, immediately your quantum gate operations and following through the Schrödinger equation, we are getting this kind of all of the states that could be represented by the system. And when you read it at some state, that becomes a reality. So the algorithm must be devised in such a way that you hopefully what that you read at the end, that is the reality, the correct that you want to get. And that was the quantum algorithm would come about. So what is this quantum speed up due to the access, basically the enormous Hilbert space that you get from your quantum system? There has been a lot of algorithms that have been written throughout the years that helps for engineering applications. We have right now the Self algorithm, solution of sparse linear algebraic equations, and Monte Carlo sampling. These are the algorithms have proven that to have quantum advantage. And what we have done, we have been using this to say, okay, these are the quantum ready applications of how we can look at the physics of engineering and sciences to see that how we can use it. But I work in the field of fluid dynamics, turbulence, and combustion. We said, okay, which problem can we investigate with this? So one of the problems that we looked at, is the problem of turbulent mixing and reaction, in which we have a system like this, in which you have some reactants, fuel and oxidizer coming into the reactor, go through it and go through some sort of mixing and chemical reaction. Now, in the context of homogeneous turbulence, we can write a differential equation that talks about the probability density function of all of the reactant species in this system. And in fact, the leader in this field is Professor Cesar de Pazo, who is in Spain, and he had worked. He's one of the leaders in development of probability density function calculations for turbulent reacting fluid, and for which these equations that I'm not going to go through it, but you can solve it by Monte Carlo methods. So when you solve them, and people have been doing them for the past several decades in engineering, this is the kind of simulation, the kind of result that you get. You would have, in this case, the amount of the fuel being converted through along the reactors and the kind of errors that you would get. So what happens with the classical computing, this error goes in as a 1 at the square root of the number of Monte Carlo particles that describe the physics. And then, but if you do with the quantum algorithm, and this is by the quantum, my quantum colleagues who have developed the quantum algorithms for the sampling for the same thing, using that algorithm, of course, you get the same results. However, in that case, the error is much, much faster with the number of the particles that are being used. So if you are doing it in typical calculations, you can, depending what kind of a quantum computer you have in hand, what you would kind of have as you want to do in the simulations, you would have something like, with the blue curve with error rate would scale down with the classical computer, and this other one, the red one, the error scaling for the quantum computer. Now, if you're working in a kind of field, this is a simple homogeneous mixing and reactor in the type of combustion chamber that we are typically working on. If these machines are available, this kind of a speed up could be very advantageous for our kinds of calculations. Now, what is happening? There's many good things about quantum computers, but what are the problems with this? What is with this, this universal digital quantum computing? What is the problem with that? But the fact of the matter is that whatever advantages that these quantum computers have, they could also can cause disadvantages. The interaction of this qubit with outside, all the noise, it can cause with, loss of coherence. It can have the vibrations. So all of this thing could have problems to allow these computers to be used for the general applications and the business. People at IBM, Google's are working on this problem, and progress is being made every day. Now, okay, so what can we do in the meantime? What are the the kind of alternative do we have until we have a totally noise-free quantum computers? You would know, as discussed in the previous talks, these NISQ machines, in which we would have a level of noise that maybe there's some level of noise, we can tolerate it for some sort of a computation. And this is one of the machines that right now it has been showing a lot of promise for some applications. There are the set of hybrid quantum classical computations. These are for some cases in which you use the quantum computation for some part of it, and then you go with the classical computation for the other part. Then there is the class of analog simulators, the companies like D-Wave and others, and and this is people who are in this business who are debating about the quantum advantage of these simulators, these machines, but nevertheless they have used for some of the problems in science and engineering, optimization, linear algebra, machine learning. Now, the fourth one, which I think is right now is the most exciting one, is this quantum-inspired calculations. And these are the kind of, as we had, as Ignacio talked about it in his talk, we want to take advantage of the development in the many-body physics. There's been a lot of advantage in many-body physics. And, by dealing with the Schrodinger equation and from my body, we want to see that if we can use them for the kind of problems in solving the Navier-Stokes, reaction diffusion equations, or any other. Now, please note that, although my interest is in Navier-Stokes and reaction diffusion, this could be used for any kind of classical problems that, in fact, given by differential equation. And this is this quantum-inspired application. One of the major development has been done in this business for the past decade or so, and quickly moving into the classical community is the area of tensor networking. This tensor networking, that you have a large number of atoms that you have to look at this interaction. You look at this the correlations of the different sizes, and then you want to say, we have this parameter, the compression parameters, to control the amount of this captured quantum correlations that are with it. So we have a large number of atoms, that they have a large amount of interaction with them, with the idea of tensor networking and, in decomposing them to a smaller network, we wanted to see if this thing can be used for the actual problems. And it happens, as I've been working in the field of turbulence for over 30 years, in this business, there is a lot of correlation between eddies, turbulent eddies of different sizes. So the way that we want to be looking at this is that, any kind of a field, this is given by this tensor of order n. This tensor, the Hilbert space associated with this tensor could be decomposed, for example, at the two Hilbert spaces. The tensor network of these two Hilbert spaces, and this can be represented in reality. By the amount of energy that are related, that is contained between each one of those things. But rather than considering the full energy of this, we can look at a portion of it. So we look at a smaller part of the Hilbert space where this fluid dynamic transport lives. So we have a large space in which the whole thing that we consider, and everybody, including myself, when we do these calculations, we're looking at the whole bigger scale. But the ideas from the many-body physics telling us that you look at a smaller subspace for which you can do the computations. So the way that it works, if you have, a big system, and then you do a whole, to just describe them in a simple way, although computational is not done that way, is a lot more computationally efficient. By the series of SVDs and contraction, SVDs and contraction, this original big tensor could be as an ensemble of this smaller tensors, and then your physical transport equations goes on between all of these tensors. The transport equations are each one of these sites obey that transport equation, solving them, and by truncating it, the amount of the bounds that they have between the scale, you can be looking at a smaller domain for which you do your computations. And this is essentially what the idea of this is. And how to show the advantage of these quantum-inspired algorithms, what we have done, we have considered the case of Taylor-Green vortex is a three-dimensional incompressible turbulent flow that obeyed by the Navier-Stokes calculations. And on the top shows the transport of the vorticity that come from the large scale and these vertical structures as the flow develops. and with a smaller cubic vortices, and then the effect of turbulence, making these vortices to become smaller and smaller. And that's what the physics of turbulence is. You have the formation of the large-scale vortices and coming and breaking down into a smaller dissipating eddies, where the dissipation of turbulence will occur. Now, this thing that is called DNS, direct numerical simulations, these are the calculations order of it, mega hours in today's fastest supercomputer, very large resolution. You say, well, I don't want to be doing it with this large resolution. I don't have enough supercomputing power. Then you can do this under-resolved DNS on the bottom. When you do this, you have a numerical algorithm for whatever reason doesn't blow up, but it is under-resolved. You're seeing that you're not capturing. You're not capturing the correct physics. I mean, the kind of the dissipation that you get at a smaller scale, is very different from what you would get with a full-scale simulations. So what would happen with this quantum-inspired methodologies, which has the same degree of freedom, as under-resolved DNS, you are getting a situation in which the physics is a lot more closer to what the reality is. And this is really advantageous and, kind of revolutionary in the field of fluid dynamics, that you can be simulating this kind of a thing in a much less computational degree of freedom, but capturing the essential physics. So let me show you where this thing was called, something in this business called the Schmidt spectra of things. So what you see on this scale is all the scales, all the scales that we actually would require in a simulations. And here with this dash curve that I'm showing in all of these cases, this is all the 99% of the energy of interaction between eddies is occurring. So if you look at this, at the most in any of this, for example, if you look at any of these things, you will see that, for example, here, this is the amount of the scale that you need. So as long as you can resolve this, you don't need all of this other range of scale that we typically do in our computations. And that's what happens in the field of CFD. Computational fluid dynamic people always worry about the grids, large grid, resolving the scale. And what this kind of thing is saying that, we want to resolve the scale is fine, but this amount of energy that is dead, it might be wasted. This is the amount of scale that what you need. And that's what this tensor networking would allow you to capture. And you're applying them for other, kind of more complicated flow. This is turbulent shear flow, in which you have the vertical structure happening, and this structures with, formation of these vortices, large-scale vortices, and they transfer, they go through the pairing throughout the domain. And if you look at between the direct numerical simulations and the quantum-inspired calculation, you see the dynamic pretty much captured in both of them. But if you look at the under-resolved DNS, you would see there is, even though you're seeing the vertical structures, you are not seeing the same, things happening at the same time. So this is, for example, the pairing of the vortices, whereas in this one, it hasn't happened. So the instabilities of the flow that are being, is because of the physics of the problem is not being captured by this under-resolved simulations. And then if you look at some of the things that turbulence people are interested in, looking at this, for example, called Reynolds stresses, a quantity that any turbulent expert would be interested to find out. The DNS quantum-inspired tensor network are capturing them. But if you look at this other one, you would see that this physics, this statistical property of the thing is not being captured. So you would see that, for example, at some region, that the problem has to be, like as you would see in this case, the whole thing should be positive or negative. This one is not being predicting it. So that's what's happening with this business. And I'm thinking that this business from quantum inspired would be something that would have major advantages in the years to come. So as far as the future of this thing is concerned, at least the way I'm looking at it, and that the other two colleagues in the panel are better experts on this. They can correct me or not. But you know where we are right now and where we hoping to be in the future. You know, so the whole idea is to have a large number of qubits and to be at the point that to totally fault tolerance. So that's what. But in the meantime, in this community, what we need to be doing is that to understand that quantum computing is going to be there. It's very different from where it was 20 years ago. A large number of us, we didn't know that where is the future of this. So what we need to do, at least from engineering point of view, we need to identify areas in which quantum algorithm can be useful, either by direct manner or in a hybrid manner. And please understand that, in engineering communities, even though, in engineering communities, we are learning about computations, this is the time to pushing our students to understand about, where this business is. So they have to understand quantum algorithm, quantum computers. I'm really glad to see that places like IBM, they have this schools for, teaching the students how to use Qiskit. So this doesn't have to be introduced to them either in the direct quantum ready or learn about quantum inspired algorithm. Just a lot of things coming from many body physics that are changing the way this classical computation can be done. So there are many projects for analog simulations. You would see that places like NASA are using this analog simulations of quantum. And what I think that the quantum algorithms would definitely be playing a major role on this spot. Now here at this end, what I'd like to say that in engineering community we have been very active in talking about the quantum prospect. I organized this workshop some a couple of years, actually not many years ago at NASA with a NASA report coming out. And now also this report was published in AIAA journal. But right now AIAA journal is having another a special issue dealing with this problem of quantum computing. So this special issue is on its way to be coming out within this year or next, in which a large number of our quantum colleagues are contributing to that. At this point, I'd like to stop and thank you, and also again saying that this is a very difficult field, and I have had the honor of working with a very good group of quantum physicists and quantum engineers and the algorithm developers on this business. Thank you for your attention.
Hello, thank you, Payman, thank you. Very, very interesting. Now we have completed the session. As I said at the beginning, we went from the theory to the future of the device, and now applications that are not intuitive directly in fluid mechanics. Okay, so there is a big distance that we have gone from one to the other. So now we are going to be in a colloquium. We don't have a lot of time. We have like 15 minutes or something like this for some questions. And I already got some questions from the network, okay? And we are broadcasting this event. And there is one about, we have mentioned several times quantum communication. And probably this is, Ignacio can answer about this one probably. What is the property that we are really exploiting? What is the quantum property that we exploit in quantum communication? We have discussed a lot about the qubits, which is in the quantum computing, but what is behind the quantum communication? I guess it goes with entanglement or something like this.
Okay, so the idea is that information can be processed using quantum physics. This gives rise to quantum computation, but it can be transmitted using quantum physics, and this gives rise to quantum communication. So in other words, you can put information into superpositions and send from one place to another. And there are several advantages two especially. So the first one is that because this information is in terms of superposition, if somebody wants to read the information, will change it, and therefore people who are trying to do the communication will notice that. And so this gives a direct way of sending communication in an hackable way. So this way cannot be hacked, and therefore it's a secure way of sending information. The second part, which is a bit more complicated, it is in the same way that quantum computers can have quantum advantage, meaning that it can process information more efficiently, more faster than a classical computer. Also in quantum communication, we can solve some problems of communication more efficiently using superposition. A typical example is the agenda problem. You have an agenda, I have an agenda, and we want to find a date to meet. One possibility is that I send my whole agenda and then you check and tell me when you're free. Well, if you use quantum superpositions, you use these qubits in order to communicate, this can be done in a much more efficient way, meaning that we have to send less photons through the fibers.
Yes. Very, very interesting. Okay. So there is another question here that I have. And I guess this one goes with Dario. Where are we now in coherence time? Okay, how long we are able to maintain a machine in a quantum state? So what is the...
The answer to that is a function of the technology you use. You know, ions, as an example, have very long coherence times. If you use superconducting technology, the coherence time is less, but they have other properties. But I'll give you the answer for superconducting technology and to give you a sense of progress. So when Nakamura-san, demonstrated the first sort of like qubit device when he was at MEC in Japan in 1999, the coherence time of a device was 1 nanosecond. In the systems that we have online, they are, routinely in the 100+ microseconds. Okay. Experimentally, we've demonstrated things that now are in the millisecond, right? In that range, getting in there. So what you're seeing here is over the course of, let's say 20 years, a few orders of magnitude improvement. But I would say for superconductor technology, you can expect hundreds of microseconds, and definitely this decade, getting into now the millisecond regime.
Okay. Thank you, Dario. So we have to be very fast in computing what we have to compute. Result.
Well, but I mean, remember, this is linked. The story on that is that's an element of it. But then it's like, how do you can you start implementing the error mitigation? It's also the fidelity of the devices. So you have a lot of fidelity and you have enough number of qubits, you can start implementing, error mitigation and ultimately error correction. So, all of these things are coupled, but, you got to bring all of it together to be able to compute over larger and larger circuits.
And also you include the technology that you are developing, that is the circuit knighting, also cutting the circuits.
That's right. So this, you can essentially significantly increase the length of the circuits by being sophisticated about where are the, strongly entangled parts of the problem that you got to run the quantum computer. There are other things that are more weakly entangled that you can use a classical computer to do efficiently, even if it's exponentially costly. Because remember, we do have a lot of classical computing power. It's not like we have zero. So you can be clever in how you structure, partition the algorithms. So this technique of circuit knitting is a good example of that. How do you stitch multiple quantum circuits that are being run potentially in parallel, and you stitch them classically with one another?
Mm-hmm. Okay. So let me get another question for Dr. Gibby Payman. You have described how you can model Navier-Stokes equations using the properties of quantum information theory. But at this moment, I guess you are running that simulation in a classical computer. Do you see, when you see yourself running this in a quantum computer? Because that will be the end goal, I guess.
Right, that is a very, very good question. All of the calculation demonstrations we have done, they were all being done on a classical computer. Yeah. However, when you show those demonstrations, you're showing the demonstration of the speed up and the rate of the speed up. So, I mean, the same thing with anything else, like a Grover algorithm or, or with any other search algorithm that has been out there that have been demonstrated on a classical computer. You can just show those algorithms, look at the complexity, the speed up to see how it works. So the first part of my calculation that was quantum ready, those are demonstrated that it has a quantum advantage. So when the quantum computers are out there, or when we are good enough to run them, we can show that advantage. Of course, when you want to compare them with a classical computer, you have to know which quantum and which classical. You know what I mean? Depending how many qubits on which one and what is the other one. But it is their speed, the speed that you are interested in. So the first one, there is no, it's proven that it's going to work out very well in quantum computing. The second part, no. The second part that what we have done, it has been all classical, but it's quantum. But a lot of my colleagues who are in this business, they are all in the process of showing that this tensor networking, product state, all of these things are very, very convenient for quantum computation. When the quantum algorithms are done, these algorithms, that coming out from tensor networking, they are much more convenient to be used in the quantum computer than the typical classical schemes like finite difference, finite volume, or other methods that we use in computational fluid dynamics.
Okay, thank you. I got another. We lost you. I got another question here in the system that says that what is the status of photonic computing? I don't know how to interpret this. It's like quantum computing with photons, or is one of the implementation of quantum computing done with photons? Who can help me to answer that question?
Well, I can help you if you want. So there are many platforms, I have mentioned that. And so the most famous are ions, superconducting qubits, and now neutral atoms. But there are other ones based on quantum dots, on NV centers. And there is one which are photons. And each of them has their pros and the cons. So the photons, they're very cheap to produce. So in fact, in the light that is going to your eyes, there are 10 to the 20 photons now per second coming. So they're very and so you can store the qubit in the polarization of a photon, which is kind of like a spin. So it can be like horizontal, vertical polarization and superposition. So it's very simple to create photons. It's very simple to create polarizations and change polarizations, but there is very difficult. First of all, the photons move very fast. Okay, so they go away. And so it's very hard to detect them. And so that's why the quantum computation with photons, if you want to use it in the standard model for quantum computation, is pretty hard, okay? Because photons will not be detected, the photon detection efficiency is very low, and so on. So there are many reasons. However, what people have figured out is that maybe not for quantum computation, but for something called quantum simulation, something related, photons could be very useful. And in fact, there have been some experiments that have appeared in the newspapers during the last years or months in which people found a supremacy with photons. Namely, they figure out some task that is not related to quantum computation, is some other task, a very artificial and academic task that if you try to solve it with a classical computer would take ages. However, with the photons, then they can solve it in seconds or minutes. So the situation, let's say, in the sense of advantage is very good. However, it's not very clear that this can be used to build a real quantum computer that solves the problems that we know. There are some other setups. There is a company in California, very well known, PsiQuantum, that is building quantum computers. They have raised $500 million for that, and they're very secret. So we don't know what they're doing, but let's hope that they also at some point come up with a quantum computer. But that's very mysterious at the moment.
There's a lot of excitement in this. Actually, there is a question from one person that is listening to us. Said, I am an engineer, I am a mathematician. I want to go into quantum. What should I do? That's the question I got. Where should I go? Should I buy a book, a quantum book, or should I go to university? What should I do? Okay, it's attracting a lot of interest. So where do we go to learn? Do we have the real curricula?
All of the above. University is always a wonderful thing to do, and getting that formal education. But one of the wonderful things too is like now there's a community. That's why I was sharing some example, right? So if you could just go to Qiskit.org as an example, You'll see a plethora of information there because it's a large community of people that have these open textbooks that are free. There's like, lectures, seminar series. There's a community in which you can write your first program. There's online access to these quantum systems where you can write your own Hello World example on that. There's now even certifications, online courses. So there's so much. So that's what I would say. Just start there. If you're curious about it, go to qiskit.org and look at it. And but obviously more and more, one of the exciting things in universities, you're seeing more and more curriculums being developed. Everything from undergraduate to masters and so on these fields. So more and more space is available. And on YouTube, there's also wonderful channels too with lectures and series on this. So there's a lot.
Okay.
Yeah, within the past few years, there has been a very large number of very good textbooks have appeared. I mean, in the past 5 years, large number of very textbooks that they start from very basic. At some universities like us, we now in the final stage of approving a curriculum for bachelor's degree in quantum computing. So we have students who can get a degree in quantum computing. Those courses being offered, many people coming and taking them from outside of the university, and we are also taking that process of hopefully developing a PhD program in quantum computing. A lot of universities are developing them, and people are visiting them. We have a Pittsburgh Quantum Institute that we offer a lot of seminars on this. For people who want to learn, it's not available.
Yeah. No, I see also here many universities increasing the curriculum in quantum. So I'm going to close with a question that is a little bit philosophical. It comes from me. When you look at the development of the classical computer and the Moore law, one can think that the reason it went so fast is because the value into the economy came very fast. In the moment you have the first computer, you were able to perform tasks. And this incentivized the private money to invest and get the benefit and reinvest the benefit, creating a virtual circle that created development that was very fast. The question here is, are we going to see this in quantum? Because until now, this is mainly still research effort by institutions, in some cases private, like IBM, but public entities, research centers, etc. And until probably we don't see our economical return, it will not jump into the scale of the virtual circle that we saw in the classical computing. Do we see this close? Is in the 5 years? Is in the 10 years? It will be in simulation probably, because when we have been listening the examples, many body problems, etc., where you have exponential speed up, that's the area where we are going to see this, where we are going to see this quantum advantage and real value created in the economy. Who guessed that? Who's going to guess that? That's a difficult question. It's almost philosophical difficult.
Well, I'll make a couple of comments if you like. So first of all, in the classical comparison, it's not true that the value was understood by all, right? I mean, if the early computers were very limited, right, within the context of military applications and intelligence and so on, if you ask people around, what does this do? What do these computers do? People thought like, well, they help us, break codes and calculate ballistic trajectories or something. Like they couldn't imagine all the possibilities around that because they were like national efforts and some of them quasi-secret. So it actually took some time until that started diffusing more and more through the economy. But in contrast to that, right, like I think the interesting aspect is like, why is all the money being invested right now in quantum if quantum machines cannot do things better than classical machines? It's like, because we know the past. We know that computing really matters. We know that this form of representing information is truly novel and special. So there's plenty of institutions around the world that are willing to invest ahead for future economic returns, right? Now, if you say it's 50 years out, well, that's hard for the private sector to do, right? I mean, universities in the context of institutions like I am part of, like the National Science Foundation and things like that, then that's good. That's what it's supposed to do, like looking way, way ahead, right? Or a place like Max Planck, right? That's its purpose. But we're no longer looking at a horizon that is that far out. And then to answer your question is to say, well, why not? I always say that there's already a quantum industry, number one, that the first example of application is the field of R&D. And you say, well, is that a market? It's like, of course it's a market. Like when people build like an accelerator, a particle accelerator, is like, is that a market? Yeah, sure. There's people who build it, sustain it, maintain it, they provide it. It's part of the scientific equipment.
By a machine.
It's happening already. It's happening already around that, like, because it's a scientific instrument that exquisitely controls quantum information and allows you to explore these things. So, in an advanced economy, 2% of GDP is spent on R&D easily, right? I mean, in the United States, it's a higher number than that. So a fraction of that is going to be spent on quantum. It's already happening. So there's plenty of opportunity to grow on that. Now, to enter into sort of like beyond the R&D domain, you have to demonstrate, you have to build a big enough machine and sophisticated enough that you can solve practical problems for business. And that's where our guess, I agree with Ignacio, is that the world of materials, which touch the industrial sector, is probably the first example where that will happen. And you're seeing companies already investing and developing teams around this because they see that the horizon of impact is going to be within this decade, right? And like I say, it is routine for large companies that rely on R&D and innovation to start doing things over the horizon of a decade. Like many companies, if you say, hey, the impact is a decade, they're not like, oh my God, that's impossible, that's too far away. They say, sure, let's get started. Maybe we won't put 100 people on it, but we will start with a small team and let's start working on that. So that's what we're seeing right now. And there's plenty of money in this field from government, from venture capital, from major technology companies, that's being invested. Not all of it is going to be successful. I guarantee you that. There's many things are not going to succeed, because just to close, one of the things is that this is an incredibly sophisticated and difficult technology. And the semiconductor example is a good one. People grossly underestimate how much money you need to put to build a quantum computer, a system, and how long you're going to have to do this for. So people need to go with their eyes wide open. It's a long endeavor.
Thank you, Dario. So, Ignacio, you wanted to say something?
Yeah, so I very much agree with what Dario was saying. I would add something that I think that maybe it doesn't have an impact right now, but it will have impact. So, I mean, I always say when they ask me, so what is the most important application of quantum computing? I always say, I don't know, but I mean, I know that I don't know. So I know that the most important is to be discovered. And if we look back, I mean, this has always been like that. We are in a very special moment. We have a device that we know that can do something better than any supercomputer. And then any supercomputer would take, I mean, years and years and years. And with this device that we have on our tables, it can solve it much faster. However, we don't know, I mean, where this could be useful. That's what you were asking. What are the applications? The same thing happened with the laser. When it was discovered, it was a solution looking for a problem, basically, at that time. And just let me give you one example that is very close to my heart. So everybody is now thinking that the quantum computer would solve problems much faster than anything else, and that's the whole goal of quantum computation. However, a couple of years ago, three years ago, some computer scientists came up with an idea that if we have a quantum computer, even if it's noisy, it could be used in order to certify random numbers. And that sounds very weird. And so what is that? Well, if you're playing Lotto and somebody gives you the number, announce the number, how do you know that this number is really random? And it was not generated beforehand, told to some people. These people bought this ticket and then they won the Lotto. It's impossible in our classical world to certify that the number is random. I give you 01110. Is it random or not? Did I know it beforehand? However, with a quantum computer, it turns out that you can certify random numbers. You can make sure that some number that comes and that's generated, it never existed before. And you say, well, okay, to play Lotto. Well, no, I mean, there are applications where when you can trust the generation of random number can have enormous applications. So people are talking about blockchain, that it can replace data mining. And if this was true, I don't know if it's going to be true, but if this was true, there would be a lot of energy saved just because of that. So what I'm saying is that, I mean, applications that we cannot even imagine now, because we have the devices that Dario is building, now we can test it, try them. And of course, they will be useful for quantum simulation. We know that, but there are many other things that we want to explore and can explore. And so it's a wonderful moment for people like me, scientists, but also for companies and industry and startups that they can try to find some application. And I think that this will keep us alive for a long while.
Okay, good. So we have
if I may add one sentence, as I agree with my co-panelists, one of the things, if you want to bridge that cycle that there is in a classical computing, as the way it is, a major part is applications. When you have to apply them for computations and demonstrate, those demonstrations, that would be a major part. The more
you should talk to the microphone. When you talk to the right, we hear you better. The other side.
Okay.
That's good. That's good.
A major part of this whole thing is the application of this, this machines. If you can demonstrate the application, that's going to help with that cycle, where that cycle is going to go. If you look at the field of classical computing, supercomputers right now, a major part of the United States supercomputers are being used for CFD, for turbulence calculations, for problems aerodynamic propulsions. Those kind of demonstrations have to be made, and at least that should be demonstrated it can be used on those supercomputers, and that would be helping it to maintain that cycle.
Good. Okay. Now, this is the last question because we need to finish here. We finish here. Okay. So I got just the last one, I guess it's for Dario. Can we build a bigger computer with smaller chips putting that together? I guess the answer is yes, because you have shown them in your chart.
That's kind of what I was showing. I mean, they won't go smaller, but in the end, there's a field of size of chip that is limited by the lithography equipment, complicated answer. But basically, there's a limit of a size of the chip that you realistically want to be able to do if you want to exercise the planar process efficiently. So then you got to have to stitch many processors together. Yeah. And that's kind of what I alluded to, that we've made a lot of progress on the ability to stitch them first classically, then with quantum links are very, very short distance, very high fidelity, very high quality, very fast. And then also to start building these quantum communication links over larger and larger distance. So the future certainly of quantum systems is based on modularity, right? First, three-dimensional integration, then multi-chips, all connected, and so on. And you got to build highly modular system. That's true for classical computing too, by the way. So you got to build very highly modular systems. So we're well past, like in the early version a few years ago, you would see these wire bonded, examples of that. That's long gone in terms of like state of the art, right? So now you got to be able to sort of like high level of integration, packaging is king, and signal processing is king. And then the scale of the systems is going to be essential to do that through modularity.
Thank you. Hey, we are going to finish here.
No,
thank you.
This.
Yes.
Ibm is asking for having us.
Yes, somebody is asking the charts. We'll get the charts.
We'll get the charts.
The chart. So, President, you close. You close the session. No, you close. You are the president of the academy.
I am president. Then, on behalf of the Royal Academy of Engineering, I would like to thank you for, GB, Ignacio, Dario, and you.
And Cesar too.
And Juan, and also Cesar Dopazo in Zaragoza, for the very interesting and futuristic seminar that we have had. And I hope that maybe in 5 years, we could repeat the seminar.
No, the thing is going to go faster. We'll have to repeat it in 1 year because the progress in 1 year is going to be so big that we'll have to revisit everything. I have to be optimistic.
You were talking about future, I in the fusion, nuclear energy, fusion. And we are always 25 years from the goal. I have been for 40 years.
Yes.
And always fusion is 25 years ahead.
After today. After today is 25 years.
But we have 5 years is enough to repeat this very interesting seminar in only 5 years. So, muchas gracias. Thank you very much.
Thank you very much. I will keep in touch. Thank you.
Thank you.